Shall I start the session? Shall I start the session, everyone? See. Yes, the class has started. Hi, Naveen. Hi. Good evening, Naveen. Good evening, everyone. Hope you guys are doing good, my dear. Now, see, everyone. I'm going to give you one problem, guys. See. One problem of metal forming is the last problem of introduction of metal forming. See, everyone. Quite good problem. You need to solve this. See, everyone, what is given here? Question number it is 62. Uh, the true stress versus the true stress sigma true strain epsilon of a strain hardening diagram of a strain hardening material of a strain hardening material is shown in figure okay. Young's modulus is given. Young's modulus, do you know Young's modulus, everyone? Capital E is equals to 200 gigapascal. Determine the strain at point B. Mine the strain at point B. Clear? Diagram is given to you. Okay, now see, the diagram is given like this. But it is unloaded here like this. Okay. means it is going like this, is loaded like this, then it goes like this till here, unloaded like this. Okay, like this. See, it is like this. So here values are given. This is your 500 megapascal. This value is your 100 megapascal. This point is your suppose O. This point is your A. This point is your C. This point is your B. Right? B point 1 minute. O. This point is your A. This point is your B. Like this till here. Right? So at this point, you need to calculate the strain. Strain at point B means if you draw a perpendicular from here. So at this point, what is the value of strain? This is asked in this problem. Okay, try it. Very beautiful problem. Strain at point B, which is asked. Okay, do it, everyone. Anyone got the answer? Anyone? Did you get the answer, Mukul? Mukul Manpuri, did you get the answer? Tell me. Not yet replied. Did you get the answer? No. 1 minute. Now, guys, see everyone. This is a very beautiful problem. Mukul Manpure, Naveen, hello, all of you. Are you there? See, now see, guys, 0AB. True stress versus true strain diagram of strain hardening material is shown in the figure. Modulus of elasticity is given. At this point, we need to calculate the strain. So, if suppose I'm going to find out here in the triangle, suppose I'm assuming this point as C. Okay. So, if suppose this is your theta, so you know very well this is your loading curve and this is your unloading curve. Both are parallel. The slope of, see this angle, if I am talking about, I have already teach you all these things in the basics. See, this is the loading and unloading. This is the loading, this is the unloading. So the slope of loading and unloading curve, true stress versus true strain, I made somewhere. See, so here we follow what Hooke's law. So in elastic limit, the loading curve follow Hooke's law as well as unloading curve follow Hooke's law. So remember that these two are a straight line, these two follow Hooke's law, these follow Power's law. Clear? So since these follow Hooke's law, so the slope of loading and unloading curve is modulus of elasticity. Remember that. So here if you apply suppose trigonometry, tan theta is equals to, so tan theta is equals to AC by BC. So tan theta. So tan theta is nothing but modulus of elasticity. AC is your 500 minus 100. So this is your 400 upon the strain between B and C. Right? This is the strain between Oh, sorry, I made some mistake. Actually, at point C, the strain is given, that is 0.5. This is the data given, strain at point C, and you need to calculate a strain at point B. I'm very sorry. So BC is what? BC is what? Strain B minus strain C minus strain B. So this you can write strain B, strain C minus strain B. So here modulus of elasticity is 200 into 10 to the power 3, 400 divided by EC. Strain at point C 0.5 minus strain at point B, which we need to calculate. Right. So now this value is also a 400. This is in megapascal. So I have calculated modulus of elasticity also in megapascal. Okay. So here we are getting epsilon B as what? Because this is your 2. So means 0.498. This we are getting, everyone. Did you get the answer? Clear, everyone? 0.498. I hope this part is done. Naveen, this part is done. Clear, everyone? I hope this is clear. Just please let me know this part is clear. We can now move to the next topic. Good. Naveen, done. Very good. Good. Now the next part is, everyone say. Next is your rolling operation. Next topic is your rolling operation, metal forming topic, rolling operation. That is the bulk forming rolling operation. Okay. See, everyone. What is this rolling? It is a process of, it is a metal forming process. It is a metal forming process in which desired shape is obtained by plastically deforming the raw material plastically deforming the raw material between the rolls, right? Deforming between the rolls. Okay. So now the mechanics of rolling, you can see, very good problem it is. See, let's understand all of you. If suppose this is your roller, this is the roller, my dear. Now see, this is the two roller. Suppose this is a sheet which is going to enter. This is the center. This is the center. So here, this is the sheet. This is the thickness of the sheet. Right. It is coming like this. See, this is going to happen, my dear. So this is called your initial thickness. This is your HI. This is your final thickness. This is your HF. This is your HI. This is your HF, my dear. Okay. So now let's understand some point. It is going like this. It is going like this. See. So here, if I'm talking about this distance, my dear, what is this distance, my dear? H initial. HI is the initial thickness. Initial thickness of the billet or a strip. You can also call it as a strip. Initial thickness of a strip or billet, whatever you call billet. HF is your final thickness. Billet. Delta H is your draft of the rolling process. Right, draft we calculate initial thickness minus final thickness. Always remember everyone, draft is your initial thickness minus final thickness. Clear, guys? So here you can see the H initial, this is your H final. Therefore, the difference is delta H. So half of the draft is this part, delta H by 2. Half of the draft is this part. Clear, guys? Now suppose here I am making a right angle triangle. I'm going to make a right angle triangle in this. So now if you are going to calculate this part, this distance is what? because this total distance we have is your radius, right? Total distance is your radius. This is going to be your r minus delta h by 2. If this is a triangle, this is your O, this is your A, this is your B, right? So this is your r minus delta h by 2 OB. This is OA is your radius r. If suppose I just want to calculate the angle subtended, right? Angle of deformation. It is called your angle of deformation. This is your theta. In the triangle OAB, my dear, theta is the angle subtended at deformation zone. Theta is the angle subtended at deformation zone. It is also called your bite angle. Capital R is the radius of the roller. Radius of the roller. Clear? Radius of the roller. So in triangle OAB, OAB, OAB. In triangle OAB, cos theta is equals to, my dear, cos theta is equals to cos theta is equals to base. Base is OB by OA. OB by OA. OB by OA. OB is what? OB is R minus delta H by 2. R minus delta H by 2. Divided by, और ये हो गया R. So this the formula is 1 minus delta H by 2R. 2R means diameter. If sometimes you want to calculate the bite angle, you need to use this formula. Theta is equals to cos inverse 1 minus delta H by 2R. Delta H by 2R. Okay, 1 minus delta H by 2R. This is your bite angle, okay? Note down, all of you. Please have a look and note down. I hope this is clear, everyone. Done, everyone? Clear, all of you? Mukul? Done, done, done. Have you noted down? Naveen, Mukul, all of you, tell me. Bite angle, how to find out bite angle? I hope this is clear. Now see, once the bite angle part is clear, next discussion is projected length calculation. See, the projected length. So this length is called projection. Suppose this is the your deformation, this is the curve, deformed curve. If you project it on the roller, it appears on the length AB. Therefore, AB is called your projected length LP. Right? It is called your projected length LP. Right? So if our objective is to find out the projected length, clear? Projected length, and it is also called arc strip contact length. Arc strip contact length. Arc strip contact length. See, arc strip contact length means how can we calculate? This is the LP. So in triangle AOB, if I am applying Pythagoras, right? So Pythagoras, if I am applying, my dear. So here, see, AB square plus OB square. AB square AB square plus OB square. AB square plus OB square, OA square. AB square LP square plus OB square. OB is your R minus delta H by 2 square. Or OA square means AB square means OA square R square. If we calculate this, my dear, this is going to be your R square minus R delta H plus delta H square by 2, right, is equals to R square. R square cancelled here. LP square you can write R delta H minus delta H square by 2. Clear? Now see, everyone. Here, see, delta H value is very small. If you see, R is very, very greater than delta H. And if I am multiplying into delta H, it will become more bigger, delta H square. Therefore, in front of R delta H, we consider delta H square by 2, consider 0. In front of R delta H, right? Because radius is very big. Radius is, suppose 500, then H is your 3 mm. Delta H is 3 mm. So 500 into 3, that is 1500, and 3 square is 9. So in front of 1500, we can neglect 9, right? And 9 by 2, it is a very small value, means 4.5. So that's why we neglect it. So the approximation LP square is equals to R delta H. Therefore, the projected length LP is equals to root under R delta H. Root under R delta H. Clear, everyone? This is your expression of projected length. Right. Note down, guys. Sir, it will be delta square by, I'm very sorry. Pardon. See, this value will become a very small, okay? Will become very small. Good. Very good. Done, guys? I hope this is done. Done. Done, Prathamesh, Srivastava, Prathamesh, Naveen. Good. Now see guys, one more point which I want to highlight here. Right now the problem is maximum possible draft. Suppose you have a billet of initial thickness 5 mm. So maximum, the minimum thickness you get after the deformation, HF minimum, right? So minimum thickness we can get, that's very easy. So I'm telling you one formula, expression of maximum possible draft. So maximum possible draft. This is called your delta H max. This is your mu square R. Remember that. Maximum possible draft formula is mu square R. Right. Sometimes if they ask you in the problem, you can use this. Mu is the coefficient of friction between the roller and the billet. Here mu is the coefficient of friction between the roller and billet. Okay, now after maximum possible draft, guys, draft is H initial minus H final. So you can use in place of delta H max, what you can write, H initial minus HF minimum. Then only you will get a maximum draft. Right. So it is you mu square R. If suppose you want delta HF minimum, sorry, HF minimum, delta HF minimum. Suppose the minimum thickness, it is going to be your mu square R, H initial minus mu square R. So minimum thickness obtained. This is the minimum thickness obtained. Okay. Minimum possible thickness after rolling. Right. After rolling. Right. Minimum possible thickness. Clear? Now one problem. Next problem is C. HF minimum. I hope this is clear. Now the tangential velocity of the billet, omega VR, right? VR is your V is equals to VR is equals to omega into R, or you can use pi dn by 60 meter per second, right? So this is your, my dear, VR is your tangential velocity of the roller. VR is your tangential velocity of the roller. Omega is your, you know what is omega and all. I'm not going to write angular velocity. The tangential velocity of the roller, it is in meter per second, right? This is sometimes important, right? Okay. Now, one more point. Uh, Suppose this billet is going towards this. The billet is going towards the roller with VI velocity, and it is coming out from the roller with VF velocity, right? VI and VF. So what is VI? What is VF, everyone? So VI and VF is Let's understand. Vi is your initial velocity. Means initial, not you can write the right word is velocity of the billet at the entry of the roller. Velocity of the billet at the entry of roller. At the entry of the roller. And Vf is your velocity of the billet at the exit of the roller. Velocity of the billet at the exit of the roller. Clear, my dear? And Bi and Bf is your width of the billet at the entry of the roller, initial width and final width. Bi is your initial width of the strip, and Bf is your final width of the strip. Initial width or final width of the strip. Okay, done, guys. Very good. Good, my dear. Good. Now, guys, see, applying the continuity equation, apply the continuity equation. Applying the continuity equation. What we can write? A1 V1. A1 V1 is equals to A2 V2. So area, initial area is your B initial, H initial, V initial, and final area is BF, HF, VF. So this is the one formula. On this you can see problems. Okay. So here one assumptions we taking width constant, just like in metal cutting, taking width constant. Keeping the width constant means B initial, B final. If I am cancel out, so VIHI is equals to VFHF. Okay. So here everyone see VIHI is equals to VFHF. That is very, very important. Now, one more point I want to discuss. If width constant, you can use this formula. There is one more point which is called your neutral plane. There is one plane which exists. Suppose this is the plane between these two. This is your actually neutral plane. What is the importance of this plane? This plane is called your neutral plane. The importance of this plane is the plane at which the roller velocity and the billet velocity are equal. Actually, what happens gradually when the rollers move as the roller, my dear, right? Done, guys. Good, everyone. Now, uh, neutral plane. I was talking about the neutral plane, my dear. See, neutral plane is the plane at which roller velocity and billet velocities are equal, right? Now, neutral plane, right? So, at neutral plane, roller velocity is equals to Vn. I am defining Vn is the velocity of billet at neutral plane. Velocity of billet at neutral plane. Okay. So guys, you know, and Hn is your height of the billet at neutral plane. Height of the billet at neutral plane. So height and C, how can we get this? Velocity as well as height, both we need to find. To see, guys, gradually when you increase, gradually when the billet metal enters into the roller, its height get decreased and velocity get increased. Therefore, initial height is bigger, velocity is lesser. So here remember this point that Vi is less, V neutral plane and Vf. The final velocity of the billet is initial height is more, neutral plane height is less, and final height is less. Okay. So guys, so what I want to say you, if you combine this equation, you are going to get V initial H initial is equals to Vn Hn is equals to Vf Hf. Right? This you can write in this. Right? Vi Hi is equals to Vn Hn is equals to Vf Hf. Right? This is the equation. If suppose you want to calculate Vn, velocity of the billet at neutral plane, so you can use this VIHI by VIHI by VIHI by HN is equals to VF by HN. This you can use. Now you will ask, sir, how to find out HN? HN is quite simple. That is HF plus something. Final height of the billet. Final height of the billet. I'm showing you. See, if this is your HN, right? So it is little slightly greater than final height. Okay, this is your HF, and HN is slightly bigger. So HF plus something. HF plus 0.25 delta H. 0.25 delta H. Clear? So this is the formula. If you get Hn from here, you can use Vn, velocity at the neutral, and velocity of the plate at the neutral plane is equals to the roller velocity. Right? Always remember, Vn is equals to your roller velocity. So roller velocity at neutral plane, the velocity of the roller is equals to velocity of the neutral plane. Means omega r is equals to v. If suppose sometimes omega is not given in the problem, and you have to calculate the rolling power. In that case, you can calculate the velocity of the billet at neutral plane, and with the help of because at neutral plane the roller velocity is equals to neutral plane velocity, which means we can get the tangential velocity of the billet at neutral plane. So we can equate it with omega r, and we can get the omega. Once we get the omega, we can calculate the rolling power. Right? I hope this part is clear. Clear, everyone? Good. So note down, guys. I'm giving you 2-3 minutes. Please note down everything. See all of you. Do it. Do it. Clear everyone? Done? See, done everyone? Now see. Have you noted down each and everything, guys? See, guys, now next important discussion is, I hope all these points which I have clearly written. See, noted down. Very good. Now, guys, how to calculate the rolling force and the rolling power. Before that, one more point which I missed actually. Number of passes sometimes asked in the problem. Number of passes. So this we calculate number of passes means how many times. Uh, suppose suppose your initial thickness is, my dear. Suppose your initial thickness is 30 mm and final thickness you want 3 mm. It is not possible in a single pass you will get you can directly reduce a 30 mm bar to 3 mm. There will be a reduction of 27 mm in a single pass. That is not possible. What we do? Maximum possible reduction per pass. This is called your maximum possible reduction per pass. Suppose this you have calculated, it is your 5 mm, which means in every passes there will be a reduction of 5 mm. Not more than that is not possible. Which means suppose the initial thickness is 30 mm, so in one pass you will get the final is 25. Again you put the 25 mm bar, again do the same again repeat the same process, you will get 20 mm, then 20 to 15, 15 to 10, 10 to 15. So this is how you will get the number of passes required. So we will have a direct formula to calculate number of passes. Number of passes is equals to initial thickness minus final thickness upon mu square by r, right? This is the direct formula you can use. Suppose you have to go from 30 mm to 5 mm. So therefore delta H is 25, and in one pass the reduction is mu square, that is 5 mm. 25 by 25, 25 by 5. This is your 5 mm. 5 means number of passes is 5 mm. This is how you can also calculate the number of pass. So note down this number of pass formula. Good, everyone. Good. Clear? Done, all of you? Good. Now, the next important point is the power calculation, force and power calculation. Rolling force and power calculation. This is the last topic of rolling. Rolling force and power calculation. Okay. First step, remember, first step is calculate projected area. Projected area is your projected length into width. Width is constant throughout. V initial, V final is same. Second step is your projected rolling pressure. Rolling pressure is your sigma naught into projected area. Yield stress is given. This is your yield stress. And sometimes if yield stress is not given, in that you can use mean flow stress into projected area. How can we calculate mean flow stress, my dear? Very simple formula to calculate mean flow stress. Mean flow stress is your K epsilon to the power n divided by n plus 1. You know very well. K is your strain hardening coefficient, epsilon is your true strain, n is your strain hardening exponent, and n plus 1, right? Area, projected area you can calculate. If yield stress is given, you can directly use. Sometimes roll pressure is given. If roll pressure is given, you can directly multiply roll pressure into projected area, you can get. If nothing is mentioned, calculate mean flow stress, multiply it by area, right? This is your yield stress, this is your mean flow stress, this is your projected area. So this is how you can get the rolling force. Now, after the rolling force, third step is your you need to calculate rolling torque. Rolling torque is what? Right, that is rolling force into arm length. Arm length is your A, force into A, and the value of A is your 0.5 into LP, projected length. This is how you can get rolling torque, right? Now, some students are saying, sir, power we cannot calculate by force into velocity. Yes, we can calculate, but here velocity is not constant like machining operation. Here, velocity of the billet is varying. Initially, it is VI, and gradually, as it enters into the deformation zone, its height getting decreased, and once the height getting decreased, the velocity getting increased. So, velocity is variable. We cannot use that. So here we are using another substitution method. We are using the torque into omega method, right, to calculate rolling power. So once you get torque, torque is F into arm length is A, and the value of A is 0.5 into projected length. Remember all the steps. Okay, and fourth is your rolling power. So rolling power is your 2 into torque into omega. Why 2 I have multiplied? Because two rollers are there. One top roller, one bottom roller. So therefore, two rollers, power is 2 into torque into omega. And omega, how we can calculate? I have told you, if omega is directly given, it's very good. If it is not given, with the help of neutral plane velocity, Vn is equals to omega into r. So from there, we can calculate omega. So these are the four steps you take care of calculating the rolling power and rolling torque and rolling force. Clear, all of you? Now shall we proceed for the numerical part? Clear, guys? Remember all the steps, all each and every step. Now I'm going to give you one big problem, right? By doing that problem, all your doubts are going to be cleared in a single problem. Clear? See the problem here on your computer screen. 63. A strip of 120 width and 8 thickness is rolled between the two rollers of diameter 300 mm. To get a strip of width 120 mm. There is a 10% reduction in thickness. 10% reduction in thickness. The speed of the strip at the exit, speed or velocity same here. The speed of the strip at the exit of the roller is 330 meter per minute. Okay. Assume uniform roll pressure of 200 megapascal in the deformation zone. In the deformation zone. right? The total power in kilowatt, the total rolling power in kilowatt. Do it, everyone. What required to drive the rolls? Do it, do it, do it, do it, everyone. Find out, everyone. It's a very beautiful problem. Very, very beautiful. Clear everyone? Try do it. Anyone, did you get the answer? Tell me, guys. Right, right. No problem, no problem. Naveen, take your time. That's a very beautiful problem. Take your time, no problem. Anyone got the answer? I am stuck with omega. Yes, so we can calculate the RPM with the help of Vn, velocity of the billet at neutral plane. By using that, you can calculate, guys. Still not getting the right answer? Sir, how do we don't know the RPM? Okay, let me solve. Wait. See guys, this was quite easy problem. Now let's understand. By doing this one problem, concepts are going to play. A strip of 120 width means width B दिया हुआ है 120 and thickness है 8 H initial is your 8 diameter है 300 10 10% reduction in thickness. 10% reduction in thickness means H final 10% reduction means 0.8 means 7.2 right? Fine. Clear everyone? Speed of the billet at the exit means final speed. This is your 30 meter per minute. No problem. Next data is your roll pressure is 200 megapascal. We need to calculate the power. Okay, no problem. See. So here everyone, first of all, what we can do guys, first step we are going to calculate the projected length. Step 1 is your projected length. Projected length is your root under R delta H. Root under R delta H. R is your 150 delta H initial minus final means 0.8. So projected length we are getting what guys? Sir everyone. $10.95 4 This is your LP. Next is your projected area, that is LP into B, 954 120, right? 131453 square. Now third we can calculate the force, that is pressure into projected. This is your 200 into 1314.5. What we are getting all of you? 262,906.82 Newton. Right. Now we can calculate the torque. Torque is your force into 0.5 lp. So force we have, that is your 262,906.82, 0.5. LP is your 10.954 into 10 to the power minus 3 into 10 to the power minus 3, right? Clear, everyone? So this is how we can get the torque. So till now, did everything this is clear? Because why I have converted it into 10 to the power minus 3? Because it will become in meter. Newton meter, that is the unit of standard unit of torque, because it is given in mm. So 0.5 lp means into 0.5 into 10.954 into 10 to the power minus 3. This is your 431,439.94 Newton meter. Clear, all of you? Tell me, Newton meters. This is your torque. Now omega is not given. That is a major problem, right? It is one of the beautiful problem of rolling. If a student can do this problem, he can solve any of the problem of rolling, right? Sir, is this right? Which is right? 10.95. What is this? Very good. Everyone tell me, till now, till this point, everything is clear? Till this point, everything is clear, all of you? Each and every projected length, projected area, rolling force, rolling torque, clear or not? Naveen is saying projected length. What projected length? Ah, yes. Till now, you just tell me. I cannot check individuals' answers. You just match your answer and let me know, sir, everything is correct. Right? From this till torque, our answers are matching with your answers. Okay? Just tell me. Mukulman, wrong answer. Wrong answer, Mukulman. Now, guys, our objective is to find out the omega. Without omega, we cannot. So I have told you that at neutral plane, the velocity of the billet at neutral plane, Vn is the velocity of the billet at neutral plane, is equals to omega into r. So we can calculate the velocity of the billet at neutral plane. How we can calculate? C. Velocity of the billet at neutral plane is final velocity, final height upon hn. So we have to do some mathematics, and hn, height of the neutral plane, we can calculate by using this equation. So C. So fifth step is hn is your hf plus 0.5 delta h. HF is equals to 7.2, 0.25. Delta H is what? Delta H is what? Delta H 0.8. So this we are getting 7.4 mm. Correct? Once we got Hn, now we know very well that Vn, velocity of the billet at neutral plane, is equals to Vf Hf, because exit velocity is given. That's why I'm using this equation. Agar inlet velocity, if inlet velocity were given, we would have used uh, inlet V initial H initial here. So Vf is what? Vf is your 30 meter per minute. HF is your 7.2 and HN is your 7.4. When we are solving this, we are going to get 30 into 7.2 divided by 7.4. 29.18. What was the unit? Meter per minute. If suppose I'm converting it into meter per second, divide it by 60. 0.486. Now all of you tell me, once we know velocity of the roller is equals to velocity of the billet at neutral plane is equals to omega r is equals to 0.486 omega into radius. Radius is what? Diameter is given 300, means 150. In meter it is 0.15. Correct. So now we have just the omega, guys. 0.486 divided by 0.15. 3.24. 3.24 radian per second. 3.24 radian per second. Very good, very good, very good, everyone. Suparna Das, the new student. I am seeing the name of one of the new students. Very good. Srivastav Prathamesh is the first student getting the right answer. Very good, very good, very good, very good. Amazing. Once we got the omega, now the eighth step we have. See, in one single question, the whole rolling, right? If suppose after some months, if you want to revise your rolling, you just do this single problem, everything is there, right? Sir, but HF is in mm, HN is in mm. What HF, NN, mm, NN, what you were talking about? So what happened? HF is mm, cancel out now. Whatever unit of VF, same as a unit of VN. These silly doubts I'm not going to discuss. Sir, we took VF and we took VF in a meter per second. I'm not getting your doubt. Can anyone, Naveen, can you explain Mukul what his doubt is? He is confused in the units, right? So the 7th, 8th class mathematics is. What problem you have? What problem you have? Whatever unit of final velocity, the velocity of the strip at the exit, same unit Vn. Vf was given in meter per minute. That's why we got it in meter per minute. The HF is in mm, and HN is in also HN is also in mm. So mm get cancel out. What you are? What you ask? I didn't get you out. Sometimes you guys ask very silly doubts, very silly doubts sometimes. Now we got it 8 say that is your power is your 2 into torque into omega. Torque is we have omega is 3.24. This we are getting 9340.15 watt. In kilo it is 9.34 kilowatt approximately. Right, this is your rolling power. Nine point three four kilowatt. Yeah. Clear everyone? This is the very beautiful problem. Very good. Now one more problem. Good. Another problem I'm going to give you guys. See one more problem. See everyone. In a single pass, using Steel rod. A strip of width 1 and a thickness 8 mm undergoes 10% reduction of thickness. The angle of bite in radian. Do it everyone. Bite angle. Anyone tell me the bite angle in degree, in radian as well as in degree? In both the units, tell me the answer. Anyone tell me the answer? 32, wrong answer. 3.58, that is right. Good. Right. Width is initial width 10%. The angle of bite, zero point cos inverse. Oh, sorry, it is delta H, no? Oh, sorry. 3.579 degree. Right. Into pi divided by x was 0.06 radian. Clear? Next problem, guys. Is rolled with the minimum possible thickness. Sheet that can be produced. Find out easily. Minimum possible thickness. H is right, mu square r. Right, 2.5. Now the last problem of ruling. The thickness of a plate from 30 mm using identical rules. If the coefficient of Find out everyone. Good person. 2 8 everyone. Anyone tell me the right answer, please? Minimum number of passes. Sir, 7 passes will be required. That is absolutely right. How can we calculate number of passes, my dear? H initial minus H final by mu square R. 0.1 square 150. Right, means Sorry, R is there, na? Radius is, diameter is 600, R is your 3. 6.67 means 7 passes is required. Very good, all of you. Very good, everyone. Clear, guys, all of you? Is the, I hope this is clear. No, no, not a single doubt. I hope this is clear, everyone. Very good. Wire drawing operation, right? Let's write the definition. We have 5 minutes. Wire drawing operation. Wire drawing operation. Wire drawing operation is your, it is a cooled working operation. To obtain wire from, to obtain wire from rods of bigger diameter through a die. Bigger diameter through a die. Okay. Types of stress in this, only tensile stress develop. The wire is subjected to tensile stress only. Quite simple. Suppose this is your die. And see, my dear. So here, guys, this is your die. Suppose this is your die, my dear. This is your die, right? And we are going to draw some forces. If we are going to draw some forces, right? Drawing it with the help of plier. So a wire is drawn like this. A wire is drawn. Suppose this is your initial diameter of the die, initial diameter of the billet, and this is your final diameter. This is your D initial, this is your D final. And we are going to draw, right? This is your drawing force, FD, drawing force, right? So in exams, they ask you this drawing force. So here we define one ratio. First ratio is R. R is called your drawing ratio. Drawing ratio R. This is your initial diameter, initial area by final area. Initial area of the billet upon wire. So this you can write di by df square. Right. This is your wire. This is your billet. Clear everyone? It will be like this, drawing ratio. So here a drawing force, how we calculate. So drawing force is your, drawing stress is your yield stress into ln r. R is your drawing ratio. Sometimes you can use mean flow stress. I have already told you mean flow stress into ln r. Right. Mean flow stress, how we calculate? I will show you one problem based on this. There is one problem in question bank you can do. Mean flow stress is K epsilon to the power n divided by n plus r. Generally, yield stress is given, right? So here, my dear, yield stress formula become sigma naught ln ai by af. In terms of diameter, if we are talking about, this is your 2 sigma naught ln di by df. And the rest, you know how to calculate the true strain. So whatever I taught few days back, the formula of a true strain, 5, 6 important formula I have written to calculate the true strain. So each and every things are valid here to how to get the true, right? So this is your drawing stress. Once you have the drawing stress, suppose you have this drawing stress, my dear. So whenever you multiply drawing stress with the drawing area, you will get the drawing force. So drawing force is important. It is your drawing stress into, see, into area. Which area? Final area, because you are applying force on wire. Final dimension you are applying force. That's why whenever calculating drawing force, always multiply with the final area, pi by 4 df square. Okay, this is your drawing force. Note down all of you. We can see 1, 2 problems on this. I hope this part is clear. Clear all of you? Tell me. Clear, guys? Good. Good. 67. A 10 diameter annealed. Die at a reduce the diameter by 10. The power required for the drawing process. Right. How can we calculate drawing power? Drawing power is drawing force into drawing velocity. Do it, everyone. This is the last problem of today's session. Do it, everyone, fast. Clear, guys? Still not getting the answer. Tell me. Wrong answer, guys. See, see, 10% reduction is there. Initial diameter is 10 mm. Guys, there's a 20% reduction. Error in this. Sorry, sorry. Do it, do it. 10 mm. 20% reduction means it is 8 mm, right? 800. This we are going to get what? 357 megapascal. Final diameter is 8 mm. 17.946 Newton kilo, right? 0.5. So this we are going to get 8.97 kilowatt. Is that clear, all of you? Please match you answer, everyone. Please match you answer, all of you. Clear, everyone? Done. Very good. So thank you, guys. Now I'm going to end today's session. See you tomorrow. Bye. Thank you.